Okay, well, this is practice problem number 2 for homework number 8. We're going to start as usual by restating the problem. And this problem looks almost exactly like the first practice problem where we have a pipe. We're going to see that a lot in this chapter. And we have a fluid that's flowing in and out of our pipe. We'll just define two states to make it easier to talk about what's happening. And our fluid is actually a liquid metal. It's sodium potassium at a 56% to 44% ratio. Okay, so initially going into the pipe, which I'm calling state 1, our liquid metal has a mean temperature of 335 Kelvin and a mass flow rate of 0.8 kilograms per second. And coming out, the sodium potassium has a mean temperature of 397 Kelvin and a mass flow rate of 0.8 kilograms per second. That, of course, doesn't change. Okay, so the first thing we have to do is find some properties. You're probably wondering where you would find fluid properties for sodium-potassium mixture to 56 to 44%. Well, that would be in table A.7 in the back of your book. And we're going to evaluate that at the average of our two mean temperatures. So the average of 335 and 397 is 366 Kelvin. Luckily, your table A7 in the back has an entry for 366 Kelvin. So writing those straight out from the table, we have a density of 887 kilograms per meters cubed, a thermal conductivity of 25.6 watts per meter Kelvin. We've got a kinematic viscosity, nu, of 6.52 times 10 to the negative 7th, and that's units of meters squared per second. Our Prandtl number is pretty small, 0.026, which we should expect for this very unique fluid. And we have a specific heat of 1,130 joules per kilogram Kelvin. Alrighty. So our next step, we draw a control volume. And here we'll also write what it is we're trying to find, because that guides our control volume here. Well, what we're trying to find is the total tube length we would need in order to have this outlet temperature, 397 Kelvin. Oh, I'm sorry, I forgot to state. Our pipe has a constant surface temperature of 435 Kelvin. I knew I was going to forget that. So we have a constant surface temperature condition. That's, of course, very important for these internal flow problems. So given that condition and our different mean temperatures in and out, what length would we need to achieve that outlet mean temperature? And finally, what is our heat flux at the surface at the very end of the pipe at x equals L right there? Okay, so for at least part A, our control volume is going to be the entire pipe. We're going to do an energy balance of the whole pipe and see if we can predict what the outlet mean temperature would be using the amount of heat transferred in. And for the last section, we're going to draw a control volume on the very end of the pipe. Okay, so let's talk about our approach here. How are we going to do this problem? Well, like any fluids problem, we're going to start by finding the Reynolds number, because if it's laminar or turbulent, it will make a difference. Once we know if it's laminar or turbulent, and because we have a constant surface temperature, we know that the convection heat transfer coefficient is going to find its way into our equation. So we're going to go ahead and find H after that, which will involve calculating the Nusselt number. Once we're there, then we will use our expression for the mean temperature as a function of x for a specific surface temperature case to solve for L. Then, once we have that, we're going to use our equation for the heat flux for internal flow, which we wrote several class lectures ago, and is just Newton's law of cooling, where T infinity has been replaced by T mean. This is for internal flow, and it's a local convective flux. So we'll apply this to the T mean at x equals L. Okay, so now that we know what we're doing, let's do it. Analysis. First, the Reynolds number. We have m dot. Because we have m dot, we will use this form of the Reynolds number, which is 4 m dot over pi d. And normally we have dynamic viscosity, but you can't actually look that up in the table. So instead, we're going to write that as nu times density, recalling that nu, or kinematic viscosity, is dynamic viscosity divided by density. So by multiplying by density, we are left with this term. Okay, when you plug all those numbers in, you get 44,000, which is definitely turbulent. Okay, so now we need to find our correlation. Remember, we are at the part where we're trying to find H. So something to notice is our Prandtl number is very small. Because it's so small, we can look at our different equations for, sorry, that's equation 8.6. So we're going to look at different correlations for turbulent flow in an internal system for a constant wall surface temperature. So the first one we encounter for turbulent internal flow is 8.60, but our Prandtl number must be greater than 0.7. The same is true for 8.61 and 8.62. All of those, our Prandtl number is too small to work for those correlations. So if we keep going, we're going to find that the correlations given in equation 8.64 and 8.65, which are specially designed for liquid metals, work for us. The Prandtl number isn't restricted by our specific very small Prandtl number. Okay, now this one right here is for a constant surface temperature, and this one is for a constant, this is for a constant heat flux. This is for a constant surface temperature. So we've identified the correlation that supposedly will fit our conditions. We're still going to check. Let's actually write out what that equation is. So this is equation 8.65. The Nusselt number is 5 plus 0.025 times the Peclet number raised to the 0.8. All right, and the one condition we need to be aware of is that our Peclet number must be greater than or about equal to 100. So we better calculate that Peclet number. Well, that is just equal to the Reynolds number times the Prandtl number, which is easy to remember because it has a P and an E. Peclet is like Prandtl and Reynolds. Okay, so let's calculate what that is. Whoops. For our specific case, we have 44,000 is our Reynolds number, which is turbulent, and our Prandtl number is 0.026. Combining those two things, we get 1,145, which definitely satisfies our condition that it be greater than 100. Okay, so we have the Peclet number. Let's now actually calculate our Nusselt number. So the Nusselt number is equal to HD over K of our fluid. And in this specific case is also equal to our correlation. 5 plus 0.025 times our Peclet number raised to the 0.8. So solving for H, because that's what we're after, we get H is KF over D times our correlation. So plugging in what we got for a Peclet number and our thermal conductivity of our fluid, which we looked up, and the diameter of our pipe, which we are given, we get a convection heat transfer coefficient of 7680 watts per meter squared Kelvin. Okay, we're almost there. We just need to recall at this point that we derived an equation for the mean temperature at the inlet and outlet of a fluid going through a pipe subject to a constant surface temperature boundary condition. And this is that expression right here that I'm writing. So again, to restate, this is how we determine the outlet mean temperature for a known inlet, or determine the inlet for a known outlet for a constant surface temperature condition. Okay, in our case, we actually already know both mean temperatures. What we don't know is the length. So we're going to simply solve for the length. In order to do that, we're going to take the natural log of both sides, canceling our exponent, and then solve for L, which will give us L is equal to the negative natural log of our temperature terms times, moving all these constants over, m dot Cp over the perimeter times the average convection heat transfer coefficient. All right, so we know all of this. We might be a little bit confused by H. We found this H right here being 7680, but exactly where does that apply? Is that at the very end at x equals L, or is that the average over the whole thing? Well, you'll remember that, oh dear, that H is constant in the fully developed region. And so because it is a constant, then the average and local values are essentially the same, ignoring any effects from the developing region, which we will say is small. Okay, so when we plug in our H value we have right here, we get a length of 0.9 meters. So now we just need to do part B, which is what is the heat flux at x equals L into our fluid from the surface. We've already said about, let's rewrite it. The heat flux for internal flow at any point can be written like this, where we put in the mean temperature at our specific point and H at our specific point. Well, like we just said, H is constant, so in this case it's 7680 everywhere. We know our surface temperature is 435, and we know T mean at the outlet, which is where we're trying to find the heat flux. So we simply plug those in and do that calculation, and we get 292,000 watts per meter squared, which is pretty big. All right, thanks for watching.